I'm Dima. I'm currently a data scientist in Pagaya, working in finances. But in the past, I was in the Israeli Meteorological Service, and I was a climate scientist. And we did a lot of extreme value theory or extreme value analysis in the Met Service. And that's what we're going to talk about today. So what is EVA? It's a branch of statistics that provides a theoretical framework that supports a set of techniques to deal with extreme events. And by extreme events, I don't mean the top 10th percentile of your data. I don't mean the top 5 percentile of your data. I'm usually talking about events that are outside the measured data entirely, or maybe at the very, very top of the 0.001 percentile. And why do we need EVA? Well, first of all, for climate research and meteorology, we want to predict dry periods, which can cause huge forest fires, such as we had in California a couple of years back. In finances, actuaries, and macroeconomics, we want to predict things like daily withdrawals from a bank to prevent a run on the banks, like there was in 1929 in the Great Depression. In medicine, we want to predict the likelihood of different mutations or biological processes. For example, mutations in the COVID virus, which started with the original strain and then had a couple of mutations that brought on the Delta strain, and then 52 mutations for the Omicron strain, which was predicted ahead of time using the knowledge gained by EVA, despite this being a highly improbable occurrence. But with millions of infected, the highly improbable becomes a fact. In cybersecurity, we want to assess maximum loads on infrastructure and prevent DDoS attacks by limiting access. In safety and engineering, we want to predict the maximum load on infrastructure such as bridges and prevent bridge collapses, which these nice people from South America did not do, and that's what happened. So what will we actually be talking about today? We'll start with the mathematical basis of EVA and talk a bit about the basic statistics that allows us to do all these predictions. We'll talk about the implementation, which is how do we actually use these tools to make the predictions. We'll talk about specifically the existing tools for EVA in Python and in R. I know this is PyData, but you'll have to bear with me for just a second and discuss R. And we'll talk about advanced EVA and more recent developments in the field. The field itself started around the 1950s, and most of what I'll be talking to you has been developed by the early 1960s. So when I'm saying more recent developments, that's 70s and onwards. So let's start with the mathematical basis. First of all, the bulk versus the extremes. Here is the distribution of 10-minute measurements of wind from Hadera, Israel, over 10 years. Roughly, this distribution follows the Weibull distribution, as all wind does, since it can't be negative. This is wind speed. And you'll have to believe me that over here, in the corner, we have one single measurement of 25.5 meters per second, considerably higher than any other measurement we ever had. We have good reason to believe that this is not an outlier. This is not an error in measurement. This is an actual wind event. And if we sample this Weibull distribution at this 25.5 level, we get the result that this is a 1 in 1.5 million year event. That sounds a bit unlikely, but hey, a 1 in a million happens one time, right? So what if that's what happened? Well, to eliminate this possibility, we added synthetically 100 more measurements of 25 meters per second. And now, when we look at the probability for this event, it's 1 in 460,000 years. So this is way off. We had 100 measurements of 25 meters, and our very naive model tells us that it should only happen once every 500,000 years, and not 100 times in 10 years. So the problem is that extremes don't behave in the same way that the non-extreme population behaves. We call the non-extreme population the bulk of the data, and we separate it from the extremes. And the reason is that there are often different underlying processes. For example, crime in Canada is generally very low. But when there's a hockey game, there is sometimes a hockey riot. And in a hockey riot, we can have hundreds of arrests in a single night in a town that usually has less than 10 arrests in a year. So these are clearly very unique things that do not behave the same as arrests per day during the rest of the year. So if we calculate the extremes using the bulk of the data will dominate the distribution, and any model we'll build based on the bulk of the data, or the bulk and the extreme together, will be a severe underestimate of the probability and the magnitude of extreme events. And I think it's pretty obvious why that's a very bad result. We do not want to underestimate loads and bridges, as we saw before. So we only can use the extreme events to predict other extreme events. The problem is there aren't many extreme events. So we're always in a situation where there's not a lot of data. So just looking at the data, we can't make any statements about its distribution, what's called the aparametric approach. We need to have an underlying model and know what kind of curve we're expecting to see in the distribution. And it's hard to formulate such a curve for every kind of process for which we want to explore the extremes. But FTG, which is a short for Fisher, Tippett, and Gnedenko, gave us a theorem which solves this exact problem. The FTG theorem tells us the exact distribution of the extremes regardless of the process which we are exploring. And the theorem goes thusly. The maximum of n random values drawn from any distribution becomes closer to a GEV, a generalized extreme value distribution, as n increases. This might sound a little bit confusing, but maybe a parallel will help you kind of connect the dots. This is very similar in form to the central limit theorem, which states that the mean of n random samples will tend to be closer to a standard distribution, a Gaussian, as n increases. So here we just take the maximum instead of the mean, and we get the GEV instead of the Gaussian. And what is this GEV? It's this beauty. And it's a bit complex, but we will unpack at least some of it, not all of it, in the next couple of slides. So let's start with seeing that the probability of x, which is the PDF, the probability density function, does not depend directly on x, but only on t of x. So we've got a transformation on our variable itself, which is the t of x, which is the second row. And we see that mu appears here as a parameter. That's a location parameter, a classic parameter that modifies x. If you increase x by 5, but you also increase mu by 5, you didn't do anything to this function. So this is a location parameter. We don't need to think about it any more than that. Then there's the sigma, the yellow parameter. That always appears in the denominator, and it broadens or sharpens the distribution. And therefore, we don't need to think about that too much either. We just accept that a high sigma means a broad distribution, a low sigma means a very precise distribution with the short tails. So then we have the xi parameter. I do not have a simple and easy explanation for what the xi parameter does, so we'll just call that the shape parameter because it just fundamentally changes the shape of the function. What we can say is that since it appears with a 1 over xi, we can immediately understand that there might be a problem once we set xi to be 0, because 1 over 0 is usually problematic. So if xi equals 0, we get a different simplified version of this function, which is this. This is called the Gumbel function, and it's a simplified version of the GEV, the generalized extreme value. So now let's see what happens if we look at other values of xi, specifically -1/2 and +1/2. We keep mu to be 0 and sigma to be 1. If sigma is 0, then this is a delta function, so it's not interesting. And mu, as we said, just moves the function around to the left, to the right. Again, not very interesting. So with a xi that is negative, we get what's called a reverse Weibull function. That's, again, a subset of GEV, the reverse Weibull. And the interesting thing about that is that it has a strict maximum. For example, with a xi of -1/2, a sigma of 1, and a mu of 0, you can't get a value over 2. And if the xi is positive, then there's a strict minimum. Only if xi is 0, only if we're looking at the Gumbel distribution, do you get an unbounded function. Further exploration is possible, but for now, we'll move on to the basics of implementing this technique. What can we do now that we know how the extremes are distributed? We can use a basic pipeline for exploring those extremes. We'll take a set of samples from an underlying distribution. We'll decide on a period over which we want to take the maximum. Remember that in the FTG theorem, we said that we need to take the maximum of n measurements, and it becomes closer to GEV the higher the n is. So if we have 10 years of measurements, we can take a 5-year period, and then we'll have a very big n because there will be a lot of measurements within the block, but then we'll only have 2 blocks. So we'll only have 2 data points to fit the GEV. So that's not a good idea. We could take a period of 1 week, and then we'll have lots of data points. But then the FTG theorem is not satisfied because we're not taking a large enough n, and we can't expect it to be distributed in a GEV fashion. So we'll need to take something in between. For climatology and meteorology, mostly we take 1 year, but for other applications, other periods can be relevant. And then over each period, we just extract the maximum value of the block. So how do we do it in Python? The easiest way is to import PyExtremes, a Python package that deals with extreme value analysis. You should also import pandas because PyExtremes, while being built on scikit-learn, takes a pandas series as its input. And then you read the time series. For example, here, the water levels at Battery Station in New York, which helps monitor and prevent flooding in New York. And then you create your model. It's the pyextremes.eva. And again, you initialize it with the time series that we just read. And then you run getExtremes. You specify the method. In this case, it's the block maxima method, the method we've been discussing. There are other methods which we might get to if I have some time at the end. And we specify the block size, which is 365 and a quarter days, colloquially known as a year. And then we just ask, for example, to plot extremes, and we get this beautiful graph that immediately tells us which data points are to be used down the line in the extreme value analysis, which is obviously the highest point of each year, but this gives a good visualization. It can also immediately show us that there are some gaps in our data. We might be missing some extreme events within those gaps, and we need to be mindful of that. If the gaps were very large, we'd probably want to invalidate those years where there's a large gap. But if the gaps are small, then we can assume that no maximum event appeared within those gaps. After we did that, we just fit a model. We fit a GEV distribution to the extremes by running the fit model method of the model object. And now we want to sample the distribution at specific cumulative probabilities. So we use the cumulative probability function. And in the PyExtremes package, we do it using the getSummary method. And for example, here I requested the 10, 50, 100, and 500 year return values. So even though we have less than 100 years of data, I'm counting on this method to produce a 500-year event and give me reasonable expectation on what's the 1 in 500 years water level at battery station. And I have an alpha and an n samples to run a Monte Carlo simulation, resampling the existing extreme data to get confidence intervals on all those values that I'm about to show you. By plotting the summary, I get this table, which gives me the return period, lower and upper confidence interval bounds, and for the 4 return periods that are requested. So you can see that for 10-year period, I have very narrow confidence intervals, but for the 500-year return period, while I do get a result, it has a pretty large confidence interval between 2.50 to 5.82. That's to be expected. Obviously, no amount of statistical trickery can give me very precise and correct answers to a question like, given few years of data, give me the maximum over a much larger period of time. After I do that, I'd like to explore and evaluate the model more in depth and see that despite the relatively small number of data points, I think we should get a model with a pretty good fit because we knew exactly what the shape of the model should be. So to do that, we use simply the method plot diagnostics. Again, we specify an alpha so that it can plot not just the expected values, but also confidence intervals around them using Monte Carlo. And we get a return value plot, which gives us the expected water elevation for each return period. In this case, only up to 100 years, because that's in an evaluation plot, and we only had 100 years of data. So there's no way to realistically evaluate the value we have at 500 years, since we don't have 500 years of data. But we can see it, how good the model is, at least for those first 100 years. And we get the PDF that we discussed earlier. This is a Gumbel function, if I'm not mistaken, although we don't get the left tail of it. And we also, from the same method, will get a QQ plot and a PP plot. You can see that the PP plot relies on an assumed probability for the measured events. We assume that the event that we measured once in 100 years, the largest event, has a probability of around 1% happening per year. That is not necessarily true. We could have measured within those 100 years an event that is much rarer, or maybe we did not measure any event that is that rare because we only had relatively common events within this 100-year block. So this is kind of assumed. The QQ plot, on the other hand, that's empirical. I know the quantile of each of my measurements, and I know the predicted quantile. And you can see, as expected, that the R-square is not as good for the QQ plot, though still 0.975 is a pretty good fit. So now you can answer questions like, what is the likelihood of an earthquake of magnitude 7.7 occurring within a period, let's say within the next 50 years in Israel? If you're building a house in Israel, maybe that's a question you want the answer for, especially if you know that it's proved for a magnitude 7.5 earthquake. What is the wind speed for which there is a 2% chance of occurring within a year, the 50-year wind? If you're building a skyscraper in Israel, you want to know that the windows you're building will not shatter inwards during a wind event, at least not at a 2% probability every year, which is a little bit too high, at least for my comfort. So Problem solved, right? Not so fast. One problem is that I just ran fit model, but the fact is that we can fit a curve to data in lots of different ways. There's the classical method of MLE, maximum likelihood estimation, but we can use method of moments by matching the average and the standard deviation and the third moment and the fourth moment of the theoretical distribution to our measured data. Or we can use other methods to fit. And each fitting method will give us slightly different results with slightly different upsides and downsides. And we need to be very cognizant of what it is that we want our model to be best at. There's the question of how do we evaluate the goodness of fit? After we've fit the model, we want to know whether it's a good fit. If I fit the model with MLE and then I evaluate the goodness of fit using maximum likelihood, I will get a very good result. It doesn't mean it was a very good model because you're fitting and evaluating using the same methods, and that's bad practice. Then we have the question of if our fit is not good enough, is it because we did not choose the right method? Or is it because the blocks over which we maximized weren't large enough? For example, with the hockey riots example that I alluded to before, if a hockey riot occurs every 10 years or every 15 years, and I take the annual maximum of criminality in a specific city, then most of my data is not actually from the extremes distribution, because most of the years I don't have a hockey riot, which is the only event during which Canadians become rowdy enough to be arrested. It is known. And finally, not all processes satisfy the prerequisites of the FTG theorem. Specifically, we can have one-off events that change the landscape completely. For example, after we dropped 2 nukes on Japan, that itself made it so that we never dropped a nuke again anywhere else. So if we, for example, look at the distribution of destructiveness of bombs, and we ask ourselves, how destructive is the extremes of bombs? Then after those 2 events, we will probably never see a repeat of these kinds of events. And that means that the events are not independent. I'm maybe speaking too hopefully here, but I'm an optimist at heart. So now we've already touched on EVA in Python, but we'll look more in depth at programmatically using EVA. So another package in Python is scikit-extremes. It's built on top of scikit, or scikit-learn rather, and it implements fitting the GEV by 2 methods, both the MLE and the MOM that I referred to earlier. It makes nice graphs, such as these. Again, plotting the extreme values over frequency and PDF for the extreme values. But it is largely superseded by PyExtremes, since PyExtremes took scikit-extremes and then built upon it a few very helpful methods that make it more user-friendly and generally improves usability. And unfortunately, that's it, more or less. There's a couple more packages in Python that have implementations of the GEV function, but nothing that actually deals with the pipeline of predicting extremes. In contrast, let's look at R. So in R, for univariate extreme value theory, which is when we have a single variable for which we want to look at the extreme, for example, magnitude of earthquake, we have all these libraries that deal with the block maxima approach, which is the approach we took so far, taking a block of data, choosing just the maximum from it. There's a peak over threshold approach, which is implemented by a dozen more libraries. And that's when I define an extreme not as the largest of a year, for example, but as anything that passes a certain threshold. So everything above 20 meters per second wind is defined as an extreme. And then I look only at these. For extremal index estimation approach, which is a third approach, which is a bit outdated, we have even more packages, though that maybe isn't that big of an advantage for R. And then there are several regression models that deal with extreme value analysis, and a couple of copula approach packages, which are also implementing extreme value analysis principles. And then we have bivariate extreme value theory and multivariate extreme value theory, and those are also supported in R by numerous packages, again, for numerous ways of dealing with those scenarios. And a big part of why I'm giving this talk is as a call for action for all of you developers who are here. We need more implementations in Python. What is it that we want to implement beyond the basic EVA pipeline that I've discussed so far? Well, the advanced EVA techniques that I'm going to show right now, which are none of them implemented in Python. They can be implemented from the ground up by the researcher, but obviously it's time consuming and also often suffers from different problems of interpretability and communication. One such thing is covariate adjustment. That's something I was doing a lot of in the Met service. Suppose we have data from related processes. For example, we have 5 rain gauges across the coast or coastal area of Western United States. And we want to predict the extreme rainfall in a 6th point where we don't have a rain gauge. So we know that extreme rainfall follows 2 patterns. First of all, it diminishes as I go farther away from the sea because there's more rain on the coast than there is inland. And it increases as I go up in altitude. Again, the higher places get more rainfall. So what I want is to give an X value and a Z value to each of my points, including the one where I don't have a gauge. And then using the red points, where I have measurements, hopefully quite a few years of rain measurements, I can fit a combined model, not on each of these points individually, but one that fits all the points together with a single model that has a single xi, because I assume that the shape of the distribution should be similar between all these points because they are generally in the same kind of area, climatologically speaking. And the mu and sigma that, while not necessarily fixed, are related to those covariates, to those x and z that I've defined before, the distance from the sea and the altitude. So for example, maybe I'll try a model like this, where mu is constrained to be some kind of intercept mu0, minus b times x for a positive b, and plus c times z for a positive c. Minus b because we expect the distance from the sea to decrease rainfall, and plus c because we expect the altitude to increase rainfall. And for example, in a naive model, maybe sigma will also be set to a specific sigma 0, but maybe I'll also try to play with it as well. And again, that would allow me to predict the rain, the extreme rain, in this green point. Other things that we want to be able to do in EVA is overcome some of the limitations that are inherent in the system. One of them is stationarity. We assume that our 50 years of data collected come from the same distribution. But if there is climate change, or if there is a change in the consumer patterns for my consumer application, or if there's any change in time, then in fact those data don't come from the same distribution, and I need to kind of bring them to the same level using pre-processing. But some recent advances propose a framework that does not require me to do that. I can use that data and deal with the extremes despite their time differences. There's the problem of incompatibility with machine learning. We know that machine learning doesn't work well outside the bounds of the training data. And we know that EVA can't use machine learning because there's not enough data. And there's pioneering work in that as well, in combining those fields despite those limitations. There's the problem of univariate versus multivariate distributions, which is, again, essentially a solved or a problem that's on its way to being solved, but, again, not implemented in Python. I'm unfortunately kind of out of time for Q&A, but you can ask maybe one question or two. Do we have time? Yes.
I have two. I don't know which one.
Pick the second one.
Okay, I'm going with the second. So the example that you gave us with the extreme rainfall in states, it seems to me, especially if we have not many data points, like a good case for using hierarchical Bayesian models, for instance. Do you think that this is something that would work good with this framework, and have Bayesian approaches been implemented in this area before?
The answer is yes and yes. A Bayesian approach is what you do with this kind of framework, although it is not necessary because of the relatively small number of data points and the small number of possible variables. It's possible to arrive at very similar conclusions to a Bayesian approach using a more classical approach. But again, if I were implementing it in a programmatic way, I would implement it in a Bayesian approach. Thank you very much.